Consider this standard engineering model, a uniform, straight column subjected to pure horizontal compressive forces, marked here by the red vectors, P. Standard linear finite element analysis operates on the assumption that a load only causes deformation along its direct line of action. If you push horizontally, the material should only compress horizontally. Mathematically, if we ignore axial strain, this standard linear approach predicts that a perfectly straight column will never bend, no matter how much weight you add. It suggests the column is infinitely strong. But in the physical world, real columns eventually reach a limit where they suddenly and violently bow sideways. This gap between theory and reality exists because the standard stiffness equation fails to account for the physical interaction between an axial force and a lateral deflection. While this simplification works for beams under tension, which naturally stay straight, it is a dangerous oversight for any structure under compression. To accurately predict this failure, we need to uncover the mathematical link that forces a purely axial load to recognize the beam's lateral movement. This requires us to derive a corrective term that accounts for the structure's changing shape under load, a term known as the geometric stiffness matrix. This shift will move our analysis from solving for simple displacements to solving for the stability of the entire system. By forcing the axial forces to acknowledge lateral bending, we can bridge the gap between an idealized straight line and a real-world structural collapse. We begin by looking past the entire column and focusing on the material at the exact moment it starts to deflect. Here, we've isolated an infinitesimal slice of the beam, dx. Note the compressive loads, P, acting on the ends of this slightly curved segment. As the segment bows, it develops a slope. This change in deflection represents the angle of curvature, d theta. Because the beam is now angled, the horizontal load P is no longer aligned with the material's center. It splits into two parts, a normal force and a perpendicular shear component. This perpendicular component, P sine theta, is a destabilizing force pushing directly against the side. Even at very small angles, this force performs physical work along the slope of the bend. This work is unique because it compounds. As the deflection increases, the lateral force pushing the beam outward also increases. This creates a mechanism behaving like a negative spring. Instead of pulling the beam back to center, it actively drives the material further out of alignment. To find the stability limit, we must account for this negative spring effect in the structure's overall energy balance. Buckling occurs when this infinitesimal shear force uses the beam's own curvature to overcome its internal structural resistance. Now we must integrate this microscale physical observation into a mathematical model for the entire beam. The internal elastic energy, the stiffness of the material itself, remains the same as in any standard bending problem. However, our equation for external work must expand to include the work done by that destabilizing shear force. This extra term represents the energy contribution of the axial load as the beam bends. It is the mathematical signature of the buckling phenomenon. By including this term, we are formally adding the negative spring effect into our structural analysis. To balance these forces, we apply Hamilton's principle, which allows us to find the state of the system by varying the total energy across the entire volume of the beam. By tracking the variation of the external work, we can isolate the specific energy contribution of the shear component. Isolating this integral is the key to separating buckling behavior from simple linear elastic bending. Hamilton's principle has provided the mathematical framework to capture geometric instability within the language of finite element analysis. To make this usable for computation, we have to translate these continuous energy integrals into the discrete language of nodes and elements. We do this using standard beam interpolation functions, the shape functions that describe how the beam moves between its connection points. By substituting these shape functions into our isolated energy integral, we can solve the calculus for a single element. As shown here, this substitution transforms the integral into a standalone matrix expression. This is the geometric stiffness matrix, Kg, a 4x4 array defining the element's instability. The values inside depend strictly on the physical length of the element, L. Significantly, the entire matrix scales directly with the applied axial load, P. This distinguishes Kg from the standard structural stiffness matrix, which is defined by material properties like elasticity and the moment of inertia. The geometric stiffness matrix represents pure geometry. It describes how a structure's own shape under load can lead to a loss of stiffness. We have successfully translated a complex physical instability into a neat, programmable matrix, completing our mathematical model. We now combine the structural stiffness and the geometric stiffness into a single, complete element equation. As the load P increases, the geometric stiffness is subtracted from the structural stiffness, effectively weakening the entire system. To find the exact point where the beam buckles, we examine the system's stability without any external lateral forces acting on it. We apply this by setting the external load vector, Q, to 0. This leaves us with a critical choice. Either the deflection is 0, or the combined matrix itself must be 0. If the deflection is 0, the beam is simply staying perfectly straight. We call this the trivial solution. Physical buckling occurs at the moment the determinant of the combined matrix system reaches 0. This formula defines a classic eigenvalue problem. The resulting eigenvalues give us the specific critical loads that will cause the column to fail. The associated eigenvectors tell us exactly what shape the column will take as it buckles. By incorporating the work of axial loads through Hamilton's principle, we expanded finite element analysis into a rigorous method for predicting structural collapse.